You are highly welcome to this revision session. I'm going to be very precise in this revision in preparation of your test and exam. There are topics that I'm not going to look into. There is a special work on those topics, the gas laws. But the first time work, not all of them, is going to be treated in this revision. In first term, we started with definition of chemistry. We said that chemistry is the branch of pure or physical science that studies about matter, its composition, structure, properties, uses, changes matter undergoes, and the principle underlining the changes matter undergoes. If you look at this, we repeated changes 2 times, changes and the principle. That means that the study of chemistry is all about changes. But these changes are being divided either the chemical composition of that substance, has it been altered? What I mean by altered is, has it been changed? If the chemical composition still remain the same, we will say it is a physical change. That means that no new substance is formed here. The mass of the starting substance remains the same, it does not change. That means that the process can still be reversible. We can see that in phase changes like melting, evaporating, sublimation. All this requires heat absorption. That means that we give energy for this to happen. We have condensation, freezing, deposition. Here we require cooling. That is, heat is being removed or heat is being released to the surrounding. We have dissolving, where we have salts are being dissolved inside water. This is a physical change. They can still be recovered. Something like dissolving sugar in water, we can recover it by heating to saturated solution of the sugar and allow it to cool. Then the crystals forms and we use filtration to remove the liquid and the crystals are being dried. We can use that to recover sugar. Chemical change. A chemical change results in the formation of entirely new substance. This is one of the things I want you to note here. And in chemical change, it's always accompanied by heat change. That means that either energy is being absorbed or energy is being released. And the chemical composition of that substance is entirely altered or changed. This makes it difficult to reverse it by natural means. So we can say it is irreversible, or I can even say that it is a permanent change. Examples of that include burning, where we have wood turning into ashes and smoke. Rusting, where iron reacts with oxygen in the presence of moist air. Another topic I would like us to look into is the building blocks of matter, elements, compound, and mixtures. Because everything around us is actually matter, and you know that matter is anything that has mass and can occupy space. So we can even say that matter is mass. But look at this. Matter are being classified whether they are pure or they are impure. That is why we have element, compound, and mixture. When we say element, this is the simplest pure substance. Example, gold, oxygen. They cannot be broken down further. In this view, I want you to see them as alphabet of chemistry. Compounds. Compounds are formed when two or more different elements chemically bond in a fixed ratio. Example, sodium chloride, water. If you look at sodium chloride, is 1 atom of sodium, 1 atom of chlorine. If you look at water, 2 atoms of hydrogen and 1 atom of oxygen. Their properties are entirely different from the elements that make them. For mixtures, it is a physical blend. It's just a physical joining of substances where each of the substance retains its own properties. Example, air. Salad. Salad is a heterogeneous mixture, whereas air is a homogeneous mixture. What I mean by homogeneous is that the composition is uniform. I'm not saying that it's fixed, but the composition is uniform. So it is colorless. But salad has green, red, and other color over there. And note these mixtures components can be separated by physical means because the properties are still there. The properties of each of the constituents are still there. Chemical compounds has fixed formula, but mixture does not have fixed formula. We normally use percentage to represent them, and that percentage varies from one type of mixture to another. The third topic I want us to look into is the particle level of chemical substances, which is atoms, molecules, and ions. To understand matter, we must look at its smallest unit. We have the atom, which is the smallest unit of an element that can take part in a chemical reaction. It can be dependent atom or it can be independent atoms. In atom, we have three subparticles we majorly look into. One of them is protons. It is a positively charged particle found in the nucleus. It was discovered by Ernest Rutherford through his alpha bombardment on gold foil. Neutrons, no charge, found in the nucleus just as protons are found in the nucleus. It was discovered by James Chadwick using alpha bombardment on beryllium. The protons and the neutrons joined together give us what we call nucleons. So when we hear nucleons number, what we are looking at is the number of proton and neutron in the nucleus of an atom. Sometimes we call it mass number. Sometimes we call it atomic mass number. Sometimes we call it atomic mass. The mass of proton and neutron using atomic mass unit is said to be 1. The proton number, that's the number of protons in the nucleus of an atom, is what we call atomic number. But if we have atom to be neutral, as we believe that atoms are neutral, then that means that the number of protons should also be equivalent to the number of the negatively charged particles, since we have already agreed that protons is positive. So we introduce electrons. Electrons are negatively charged particles. They orbit around the nucleus and they are responsible for chemical reaction. It was discovered by J.J. Thomson using his cathode ray experiment. Remember, I said atomic number is the total number of protons in the nucleus of an atom. And atoms are said to be neutral. So the number of protons should also be equal to the number of electrons. So atomic number can also be defined using electron number. From the discovering of subparticles of atom, those scientists have their own model of atom. For instance, Dalton's atomic theory lead to the model of atom called solid indivisible sphere. The discovering of electron by J.J. Thomson led to what we call plum pudding model of an atom. The discovering of proton, or let's say the nuclear charge or the nucleus of an atom, led to what we call nuclear atom by Rutherford. Whereas Bohr explaining Rutherford's work better using the planet led to what we call planetary model of an atom. Okay, that's enough for atom. You can go further and look into it. I'm still coming over for electronic configuration. Let's look into molecule. Molecule is said to be two or more atoms bonded together. They nearly have the same definition as atom. It's just that molecules can now be both for an element and for compound, whereas atom is always for an element. Example of molecule is oxygen molecule has 2 atoms of oxygen. We have water molecule has 2 atoms of hydrogen and 1 atom of oxygen. That's a compound, but O2 is an element. Remember I said that molecule can be element, it can be compound. Ions. Ions are atom or groups of atoms that has gained or lost electron. If it loses electron, it is called cation, a positive charge, typically seen in metals or ammonium ion. If it gains electrons, it is called anion, negatively charged, because it gained electron, and we normally see them in non-metals, as you can see on the screen. I have said something about atomic number and mass number, and I want you to know that we use this in electron configuration, but I just want you to note this. Atomic number is represented by Z, Mass number is represented by A. The charge number, I represent it by C, as you can see on the screen. So the number of protons, which defines the element, in a neutral atom, it is also equal to the number of electrons. Mass number. The mass number is the sum of the protons and neutrons in the nucleus. If, for instance, we want to get the formula of mass number, we just use protons plus neutrons. If I want to get the formula of atomic number, just say proton. If I want to get the formula of charge, I will say protons minus electron. That gives me the formula for charge. Electronic configuration. Electrons occupy specific regions around the nucleus based on the three main rules. The off-ball principle, here electrons fill the lowest energy orbitals first. 2. Horn's rule, electrons fill degenerate orbitals like p or d singly before pairing up. 3. Pauli exclusion principle, it says that an orbital can hold a maximum of 2 electrons with opposite spins. Quantum numbers and subshells. Remember, I said something about electron configuration. In electron configuration, we have what defines the location or position of electron. We have principal quantum number, use n to represent it. The main energy level of electron is being detected by this principal quantum number. We normally use k element to present it. Azimuthal quantum number, this is the subshell. The subshell tells the sub-energy level. We use SPDF for it. The magnetic quantum number, this tells the orientation of the orbital and tells us the number of orbitals in each subshell. For instance, S subshell has only one orbital, but P subshell has 3 orbitals and D subshell has 5 orbitals. Remember, according to Pauli exclusion principle, an orbital can hold a maximum of 2 electrons with opposite spins. If you have that at our back of our mind, that means that the number of electrons in each orbital is 2. Now, we can use that number to know the number of electrons in S subshell, which is 2, P subshell, which is 6. Remember, 2 times 3 orbitals. In this subshell, going to be 10 electrons. Hope you get that. Let's take example with sodium. The sodium that is neutral, the atomic electronic configuration is going to be 1s2, 2s2, 2p6, 3s1. If you are using k element to represent it, we convert it, it becomes 281. That means that whenever they ask you to write electronic configuration, the first you must represent is the SPDF notation. Then you convert it to the k element, where the 1 before the 1s2 represents the energy level. If you look at the number up, that is 1s2, the 2 that is up, that is the superscript. That is what the 2 is here. The 2 before the S and the 2 before the P represent the energy level. So we have 2 here, but the number ups are 2 and 6. If you join it together, will give us 8. That is how this 8 come to be. So the 1 is just for the 3s1. That's the third energy level. So you use that to convert your SPDF to k element. Don't always write k element first. First of all, write it in SPDF before you write it in k element. The ion of sodium, the electron configuration will change because one electron has been removed. So it is going to become 1s2, 2s2, 2p6. When we are writing it in k element, it's just going to be 28. Knowing electron configuration is very, very beautiful. We can still try that with chlorine. Chlorine is going to be 1s2, 2s2, 2p6, 3s2, 3p5. That is chlorine atom. But when we convert it to k element, it's going to be 2h7. 2 coming from 1s and 8 coming from 2s, 2p electrons, and 7 coming from 3s and 3p electrons. 7, as you can see. But now when it gains electron, the electron number move from 17 to 18. So we are going to have it as 1s2, 2s2, 2p6, 3s2, 3p6. So when we write it in k element, it's going to become 288. Now, if we look at this, the sodium proton number is still 11, but the electron number is 10. So since we agree that proton is positive, so we're having plus 11 minus 10, making proton to be more in sodium. So we say sodium is plus 1. But when we come to chlorine, chlorine has more electron, one electron than the proton. Remember, electron is negatively charged, so chlorine becomes minus 1. So this charge of sodium and this charge of chlorine, if you remove the sign, it becomes the valency of that particular atom. So magnesium will give out 2 electrons. That means that the valency of magnesium is 2. Oxygen will accept 2 electrons mostly. That means that the valency of oxygen is 2. Aluminium will give out 3 electrons. That means that the valency of aluminium is 3. Nitrogen will accept mostly 3 electrons. That means that the valency of nitrogen is 3. So what do you mean by this valency? This is the combining power of an atom or a species. It tells us how many electrons an atom needs to lose or gain to attain stable octet of 8. But we can only get that from its valence electron. Valence electrons are those electrons in the atom's valence shell. So oxidation state means the former charge that is being given to an atom in a compound. The sum of oxidation state in a neutral compound is always 0. If we take an example with CaSO4, calcium is plus 2, sulfur is unknown because we need to assign a charge to it. But oxygen is minus 2 because it's a highly electronegative element. Calcium is highly electropositive element. So we already know that its charge is plus 2. So we say plus 2 plus x minus 8 will give us 0. You may ask where did I get that 8? 4 times minus 2 give us minus 8. So x is plus 6. There's a code I normally use as a sum for my students. What I normally do is K-Nali plus 1, Back-Mark plus 2, aluminium plus 3. If you want to talk about zinc, plus 2. So this is what I use for my students to record the charges of these metals. Naming of compounds. We have 2 major types of compound, a binary compound and a ternary compound. When we say binary compound, it is only 2 elements, 2 different elements are present here. For ionic compound, name the metal first, then the non-metal with an IDE ending. For instance, sodium chloride. This mostly comes when we have group 1, group 2, group 3 elements bonding with non-metals. For instance, potassium, sodium, lithium, calcium, magnesium, beryllium, barium, aluminum. When they are bonding with non-metals, you don't state their oxidation state. But when we are having any binary compound formed that the highly electropositive element is not from group 1, not from group 2, not from group 3, then you need to state the oxidation state. For instance, iron 2 oxide, iron 3 oxide, copper 1 oxide, copper 2 oxide, sulfur 6 oxide. This tells us that the oxidation state of sulfur here is 6. We know that oxygen is already minus 2. If I want to rewrite, this is going to be S power of 6, oxygen power of 2. That is the valency of sulfur in this compound is 6. The valency of oxygen in this compound is 2. By crisscross, as you can see, we will have S2O6. But 2 and 6, there's a number that can still divide them. So 2 divided 2, we're going to have SO3. What about ternary compound? Apart from hydroxide, this often involve polyatomic ions, what some people may call radicals. How do we name them? Use the prefix like oxo for oxygen and the suffix like et for the central atom. So you need to know which atom is the central atom there. How do we know the central atom? We use HPICSBr and ClOF. So the one that is at the right hand side is more electronegative. So the highly electronegative, you change its name, whatever it is, you add O to it. For instance, if you have fluorine, I will call it fluoro. If it is chlorine, I will call it chloro. Since it is oxygen, I change it to oxo. Hope you get that. But for us to know the central atom must be the one that is below the highly electronegative. For instance, when we have oxygen and fluorine in the same place, fluorine will become fluoro, oxygen will become ozate. But we hardly see such compound. For instance, when we have oxygen and chlorine coming together, oxygen becomes oxo, then chlorine now becomes chlorate because chlorine is less electronegative compared to oxygen. Hope you get that. For instance, we have K2Cr2O7. It is called potassium heptaoxodichromate 6. You may ask, how do we get this? So first of all, find the oxidation state of chromium here. Look at how I get it. Remember, I sang a song before, K na li plus 1. That means the potassium here is plus 1 and is appearing 2 times. So we say plus 2 plus 2Cr plus 7O will give us 0. Now, 7 times minus 2 will give us minus 14. We have 2Cr plus 2 minus 14 will give us 0. 2Cr minus 12 will give us 0. 2Cr equals to 12. Then we divide through by 2, we will have Cr equal to 6. So that's how we got it to be dichromate 6, because there are 2 chromium here. But if it is only 1 chromium, we don't need to call any, we just leave it like I call it chromate. Hope you get that. The number of oxygen there is 7. We call it heptaoxo. Remember, oxygen here is the highly electronegative. Chemical bonding. The noble gas is the type of bond that exists between the noble gases. It's called a van der Waals force. It's a London dispersion force, and it's very, very weak, and it is found majorly in noble gas atoms. Metallic bond, sea of electrons surrounding positive metal ions. What happened here? A metal releases its electron, and its electron revolves when there is no other atom to accept the electron. So the electrostatic force of attraction that exists between the sea of electrons that have been released by the metal and the metal ion is what we mean by metallic bond. Electrostatic force of attraction that exists between a metal ion and a non-metal ion is what we call ionic bond. Remember, there must be a complete transfer of electrons from a metal to a non-metal. So the electrostatic force of attraction existing between the positively charged metal ion and the negatively charged non-metal ion as a result of complete transfer of electrons from the metal to the non-metal is what we call ionic bonding. Sometimes we can even call it electrovalent bonding. So any of the name works. Covalent bond. A covalent bond is sharing of pairs of electrons. If it is contributed equally, it is called ordinary covalent bond, and it is mostly seen in non-metals and non-metals bonding with each other. But if it is being contributed by one of the atoms, it is called dative or coordinate covalent bonding. Mind you, this dative or coordinate covalent bonding can be seen even between a metal and any molecule that has the ability to donate lone pairs of electrons. So in complex ions, we can see these coordinate bonds so many times, like tetraamine copper 2 ions, hexacyanoferrate 3 ion, hexacyanoferrate 2 ions. We can see it there. We can see it in ammonium ion. We can see it in hydrozonium ion, even in carbon 2 oxide. Look at the structure very, very well. One of the bond pair is a lone pair donated by the oxygen to form that bond. The metallic bond, ionic bond, and the covalent bond are said to be strong bond, whereas the van der Waals forces we discussed in the beginning is said to be weak force. We have other van der Waals forces, not just only London dispersion force of attraction. We have one we call dipole-dipole. This occurs when two highly electronegative non-metals combine. So one of the non-metal will assume positivity because it's lesser in electronegativity, and the other one is going to assume positivity. How does it assume that? Because electronegativity means the ability of atom to draw pairs of electrons to itself. Now, if we look at something like oxygen and hydrogen, the electronegativity scale of oxygen is said to be 3.5. That of hydrogen is approximately 2.1. You see that oxygen has higher electronegativity compared to hydrogen. So it means that oxygen is going to be drawing the electrons towards itself more than hydrogen draws. And sometimes when we look at hydrogen, it seems like there's no electron in hydrogen. So we will say that hydrogen is now positive and electron are being clustered in oxygen, making oxygen to be negative. So we have a partial positive charge for hydrogen and a partial negative charge for oxygen. That is what gives rise to what we call dipole. That is, there are two poles, a positive charge and a negative charge. Now, when we have this type of molecule formed and we have another type of molecule in the same nature coming together, we are going to have the type of bond we call dipole force of attraction. But when this dipole force of attraction is occurring between hydrogen and a highly electronegative small atomic size non-metals, we will say it is called hydrogen bonding. Look at this. It only occurs between hydrogen and fluorine, hydrogen and nitrogen, hydrogen and oxygen. It is highest in hydrogen and fluorine, lowest in hydrogen and nitrogen. Yet, water has high boiling point than hydrogen fluoride because water forms more hydrogen bond than both hydrogen fluoride and ammonia. Take that. The laws of chemical combination. We have conservation of mass. Here, mass is neither created nor destroyed in a chemical reaction. It is mostly proven using a balanced chemical equation. So we are using the masses of the equation. It is going to be always the same. If it is not the same, then that means that the law is broken. So we have definite proportion. A compound always contains the same element in the same mass ratio. That is the definite proportion. But multiple proportion, if two elements form multiple compounds, the masses of one element that combine with a fixed mass of the other are in simple whole number ratio. That's the law. Now, the question we may ask ourselves is, how will I know that these samples given to me obeys definite proportion or it is obeying multiple proportion? What I normally tell my students is, get all your sample data clearly. Let's say we have sample 1 and sample 2 and you have gotten all your samples correctly. Then let's treat them sample by sample. Let's go to sample 1. Get the mass of one of the elements, majorly the first one, divided by the same mass. Use the same mass you're using to divide the first one, divide the other one, so that you can get a unit mass, as you can see on the screen demonstrated. Okay, so you do the same thing with the other sample. If you are done with this, if you notice that the ratio of the samples are the same, so you say it's definite proportion. But if the ratios are not the same, we say it's multiple proportion. Sometimes they will tell us to find the chemical formula of those multiple proportion compounds that we have proven that they are different. Let me tell you one thing. According to me, it is advisable for you to use empirical formula to find it rather than using the ratio from that. Although for a quick work, just use the ratio to know that this is the ratio of the different masses of the other elements. You can use it to get that. But if the molar masses of the elements are being given, use empirical formula. Now you may ask me, what do I mean by empirical formula? Empirical formula is the simplest whole number ratio of an atom in a compound unit or per molecule. Whereas we have molecular formula that shows the actual number of atoms in a compound unit or a molecule. And there is a relationship between empirical formula and molecular formula. Empirical formula times a number n will give us molecular formula for you. But if you get the molar mass of empirical formula, you multiply it by n, it will give you the molecular mass of the molecular formula. So you can use that and equate, as you can see here. For instance, if they give us the shown value, what I will ask you to do, look at this question very, very well. Okay, read it carefully. Yes, I'm going to be a little bit fast because this is a revision. I'm trying to make sure that I cover so many things in just few works, so I'm not going to be going that detailing. What you need to do is first write out the element mentioned in column, as you can see I just did now. Okay, make sure the information is complete. First of all, get your data right first because it is very, very important. So what we need to do now is arrange the mass under each of the elements. As you can see, I'm picking it from the information of the question to arrange them. So you do the same thing when the question is being given to you. Or you can see the question I dropped after this. You can try it by yourself and see if you can be able to get it. Then what you're going to do is write the molar masses of the atoms. So what you're going to do now is we are going to divide the mass, whether it is in percentage or in normal gram, we divide it by the molar mass, which we call relative atomic mass. But sometimes it's better to call it relative molar mass of each of those elements, or if there is a substance like water is being added here. Okay, so when we divide it, look for the lowest among the moles, because here we have gotten the mole. When you divide mass by molar mass, you have gotten the mole. So we look for the value that is lowest among them. So what we do, we divide it by that number that is lowest among them. When we do that, if for instance you have the value as something 0.2, multiply it by 5. If you have the value to be something 0.3, multiply it by 3. General, you multiply everything by 3. If it is something 0.4, multiply general by 5. If it's something 0.5, multiply general by 2. If it is something 0.6, multiply general by 5. If it is something 0.7, multiply general by 7. If it is something 0.8, multiply general by 5. If the value is giving you 1 or 9, approximate. So now you write out those numbers as your empirical formula, mixing the compound, the substance with the numbers that are attached under each column. So that thing you have done now is what we mean by empirical formula. What are we going to do? We equate it with the molecular mass, because we need to find the molar mass of the empirical formula, then equate it to the molecular mass. Remember, the n is still there, so we multiply it by the n. The value of n multiplies the value in the empirical formula. So what are we going to do? When you multiply it, you can open up this. As you can see in this question, it becomes this. So the next one I want us to look into is mole concept. Mole concept is very, very crucial this term, and that is what we introduce. Mole concept is what we're going to see throughout our study of chemistry. So pay attention. A mole is the amount of substance containing 6.022 times 10 to the power 23 particles. And these particles we're talking about is what we call Avogadro's number. It bridges the gap between atomic mass and gram. It means that 1 mole of carbon is equal to 12 grams, and 1 mole of water is equal to 18 grams. So the unit of mole is mole. A molar mass means gram per mole, not a gram, the gram per mole. So I want you to go back and look into the formulas of moles, and always know that whenever they give you question in mole, what you should do for yourself is, first of all, look for the given, write out the given, and find your mole. Always find your mole first. Then when you have gotten your mole, look for what they asked you to search for and equate it with that. Have opportunity to download this video, watch it over and over in preparation for your exam. Thank you very much for watching to this extent.